In section 16.3, number 12, they're asking us for this vector field to find the work integral. And the thing is, they don't give us the equation of this curve at all. So we don't know the path here or anything. Our only hope is that maybe this vector field is conservative, and you can show that it is in fact conservative. If we take the partial here with respect to x, we get 2x. The partial here with respect to y, we get 2x. And since those partials are continuous on our domain, the vector field is conservative. So once we know the vector field is conservative, we have options for how to handle it. We could either find the potential function, the little f, and then evaluate it at the end point minus the start point. Another option that we have is, since f is conservative, the work is independent of path, and so we could choose any path that gets you from the point 0, 0 to the point 2 pi over 2. So we could find that line segment and do the work across there. So either way. And I'll go ahead and show the solution for both of those. Here, once we know the vector field is conservative, something that we learned is that the work around any closed path, if the vector field is conservative, that work would be 0. You could, if you don't remember that, you could take any point being the start point. It's also the end point. So f of the end point minus f of the start point, you'd get 0. All right, let me go ahead and write out these solutions. I'm going to actually talk through this part as another example. If I want to find the potential function, I'm looking for a function little f such that when I take the gradient, I get the vector field. So the partial with respect to x of our little f that we're trying to find has to be 2xy, and the partial with respect to y has to be that side. And so we start with either one of these facts and go backwards. If I integrate this with respect to x, then I'm going to get x squared over 2, the 2 divides out, times y, plus there could have been some function of y. Double check. When I take the partial with respect to x here, I do in fact get this. So we have satisfied this fact, but now we need to also satisfy this fact. So this is f so far. Then we take the partial here with respect to y, and we'd get x squared plus c prime of y. And that has to equal x squared plus sine of y, which means that c prime of y has to equal sine of y. So c of y is minus cosine of y plus a constant. So our potential function is x squared y plus c of y, where c of y is that. So x squared y minus cosine of y plus a constant. And I always check it right here to see if the gradient of f really does equal f. So now our work integral is just f of 2 pi over 2, which is 2 pi minus f of 0, 0, which is minus 1, so plus 1. Your other option of a simpler path, if I did the line segment from 0, 0 to 2 pi over 2, there is a parameterization of that. And then put that into our f and compute r prime and f dot r prime, and then integrate that from 0 to 1. And if you evaluate that, you'll get the same thing as we did over here. So how did I think to look for the fact that it was conservative? Without the equation of this curve, we wouldn't be able to compute the work unless we knew the vector field was conservative and we could use a different path or use the potential function. In problem number 35, they're asking us to show a three-dimensional version of a theorem that we have for 2 dimensions. That is, if this vector field is conservative, where P, Q, and R have continuous first-order partials, then each of these facts are true. We know that if we have 2-dimensional P, Q, then this is true. If F is conservative, then this has to be true. And when I showed you that in the video, I called these the mixed partials. And so basically it came down to Clairaut's theorem, where the mixed partials are equal as long as they're continuous. These are also mixed partials, and these are as well. Let me clarify that. If the vector field is conservative, then that means there is some little f such that the gradient of f is capital F. So the gradient of f is partial fx, partial fy, partial fz. So that means there is some f such that p is the partial of fx, q is the partial of fy, and r is the partial of fz. So let me write that down here. That p is the partial of f with respect to x, and q is the partial of f with respect to y, and r is the partial of f with respect to z. Now, if I were to take this equation and take the partial with respect to y of both sides, I would get the partial of p with respect to y is the partial of f with respect to x and y. And I could also here take the partial with respect to z. So I'd get the partial of p with respect to z equals the partial of f with respect to x and then z. So these things here, py, and pz, those are mixed partials of f. Do the same thing for each of these. So this partial with respect to x, I took the derivatives y and z, the mixed partials. Partial with respect to y, I took the derivatives x and z, the mixed partials. And so taking the partial with respect to x of both sides, I get qx and fyx. With respect to z, I get qz and fyz. Okay? Same thing here. The partials would be with respect to x and with respect to y. And from Clairaut's theorem, we know that those mixed partials, and these are actually all second derivatives. Those mixed partials are equal. So this one, where else is an xy here? Here, this one here. Those are equal. Qx then has to equal py. That's this fact here. Our other mixed partials, we have xz and zx. So those have to be equal, which means partial of p with respect to z, equals r with respect to x. That's that fact there. Which leaves us with partial yz equals partial zy. So qz equals ry. That's this fact here. So if f is a conservative vector field, each of one of these statements is true, and you'll hear me say each of these mixed partials are equal. The actual test for a conservative vector field goes the other direction, where if each of these are equal and those partials are continuous, then we get that it is conservative. We're going to learn another test for showing conservative vector field in the next section, but for now we're looking at all the mixed partials.